Okay, so we're using this bicycle example to look at how two different angles are both changing at the same time. Okay, so and that will translate to lots of just more broad problems, but this is a nice example to think about that. So we've got the pedal angle measure, and that's we translate or we the tire valve angle measure is determined based on the pedal angle measure, and then in the end we're looking at the tire valve position. Okay, something about its position. So what's the pedal angle measure? Well, we call that the original angle theta, and then the tire valve angle measure is some function of that. Last time we saw the tire valve was rotating 4 times as fast, so its angle measure was 4 times theta. So for every radian of pedal angle measure, we got 4 radians of tire valve angle measure. So how much the tire valve rotates is a function of how much the pedal rotates. And then from that, we can either talk about vertical position or horizontal position of the tire valve. And remember, if we want vertical position of the tire valve, then what has to be the argument of sine? Which angle? Pedal or tire valve? Tire valve, right? So if you want something about the position of the tire valve, then ultimately what you're putting into sine as a whole has to be the tire valve angle. And same thing if you want the horizontal position. So that's the way we think about this. So we're thinking about functions like this, or cosine of some function of theta. Okay, so what's the output? What's the output of this function? Pedal angle measure, tire valve angle measure, or valve position? Valve position. Oh, not right. Yeah, valve position is the output. Okay, what about the argument? If the output is valve position, then the argument must be valve angle. Valve angle. Okay? And then but ultimately the input is some other angle, right? Some other angle. Okay, so let's do another example here. Oops. Isn't ready. Sorry. So where do we in your book, where did we leave off? What page is that? Investigation we did last time. All right, page 281, I think it is. Page 281. So, but we're going to just cross off the 12.5, okay? So h of theta on page 281, number 5, h of theta is cosine of theta over 2. So cross off the 12.5. Okay, so in that scenario, what do you expect to see if we start rotating the pedal angle and the function is, we're talking about cosine of 1/2 theta, then what do you expect to see just about the rotation of the tire? How's it going to rotate relative to the pedal? What's the argument? The argument is 1/2 theta. And so we know that's the tire valve angle. So what do you, when I start rotating this pedal angle, what will you see? How will the tire valve rotate relative to the pedal? Half as slow, people are saying. So if the pedal goes halfway around, where will the tire valve be? Full way around? Where will the tire valve end up? Where on the circle? If I rotate the pedal half of a rotation, so to the 9 o'clock position on the circle, where will the tire valve end up? Yep, it should at the top. At the top. Okay, so the tire valve its angle is half as much, so it's rotating half as fast. Okay, if we look at cosine of cosine theta would cosine theta represent something about the pedal angle or the tire valve? Cosine theta. He wants the pedal. Cosine theta. Because theta is the angle measure of the pedal, so if you put theta into cosine, then you're going to be measuring horizontal distance of the pedal. And we know what cosine looks like. So there's one period or one full rotation. Do another period, another full rotation, and that's what it looks like. Okay, so the question is, if our argument is 1/2 theta, let's write that down. So the argument is 1/2 theta, and that's the angle measure of the tire valve, half of the pedal angle measure. Is it H? They call it H? Yes. What will that graph be like? So we'll put up the original, this function over here. Wrong one. There we go. So that's still the pedal, that's still cosine of theta, okay? So both of those are cosine of theta. The question is, what will cosine of 1/2 theta look like? Or in other words, we're tracking the horizontal position of the tire valve. Okay, so everyone take a minute and sketch it. So sketch, what will cosine 1/2 theta look like? If you were tracking the horizontal position of the tire valve, that's what cosine is, right? Cosine horizontal position. So both of those are cosine theta. We're interested in cosine of 1/2 theta. And we're looking at the tire valve and looking at its horizontal position. If it's rotating half as fast, then how long will it take to get around? What will its period be? He wants double. So just one more time, watch the tire valve. Watch the tire valve. It makes it only a quarter of the way when the pedal angle is pi. And then it makes it halfway around when the pedal angle is 2 pi. And then it needs a whole nother cycle of the pedal to finish its cycle. So draw it with your finger. Cosine of 1/2 theta. Okay, watch it. Ready? Here we go. So that's tracking the horizontal position of the tire valve as a function of the pedal angle theta. as a function of the pedal angle theta. So when you take when you take a fraction of your input angle as your argument, do you get a shorter period or a longer period? You get a longer period because that angle is moving more slowly, so it takes a longer interval to make one full rotation. If you take a multiple of that input angle, then what happens? Now that angle is rotating faster than the input angle. It's going to make it around quicker, so the period is longer or shorter? Shorter, right? That's the example we saw last time. Okay, and then to get it exactly, remember what we said? So if I do something here, so say I do 0.786. How would you find the period exactly? So now I'm taking 0.786. First of all, is the period longer or shorter? Shorter period? It's rotating. How's it rotating? 0.786. Is the argument rotating faster or slower than the input? 0.786. Slower. It's rotating slower. It's rotating about 3/4 as fast, maybe a little more than 3/4. So longer or shorter period? Longer period. It's going to take more of the input angle for the argument angle to get around. This is going to be a longer period. So exactly how much will the period be? Well, we want the argument to reach. So if we don't know the period, call it theta sub p. We need that argument. We know that we'll have that period angle when the argument reaches 2 pi. Because we know that's the period of cosine. So when the argument reaches 2 pi, we want that input angle that's going to make that happen. What input angle makes the argument reach 2 pi? 2 pi divided by 0.786. And we can get an approximation for that. $7.99, so it's just about 8. So right here, that's right there is 8 radians. And that's our period of that function, cosine of 0.786 theta. Right, longer period. What's the period of just cosine theta? Yeah, about 6.28 about, right? 2 pi. Okay, any questions on what happens? So what we're talking about is if you adjust the argument by a constant, what happens to the period? So if you take a fraction of the input angle, you get slower rotation of that argument angle, so you get a longer period. It takes more of the input angle for the argument to make it around. If you multiply by a number greater than 1, then that argument angle is rotating faster. It's going faster, so it's going to make it around quicker, and you have a shorter period. Okay, let's go on to the next investigation. And is there a problem there where it says that the tire valve angle, next investigation, it starts at pi over 4 clockwise from in quadrant 4. So what number is that? 285, number 2. Page 285, number 2. Okay, here's the scenario. So now, when the pedal angle's at the 3 o'clock position, the tire valve is where is it? It's in the 4th quadrant, pi over 4 away. Okay, so theta is still our theta is the input, and it's the pedal angle measure. And so what is the valve angle measure in terms of theta? What is the valve angle measure in terms of theta if that tire valve starts pi over 4? So from the beginning again. It starts in the 4th quadrant, pi over 4 behind. And so then as the pedal angle sweeps counterclockwise, so does the valve. But the valve is always lagging behind pi over 4. So how could you write, everyone write a expression for the valve angle measure in terms of theta, the pedal angle measure. Everyone try to do that. So how would you calculate what the valve angle measure is given the pedal angle measure? If that valve is always exactly pi over 4 behind. Is there a table for you to make? So tell me what the given angles of theta are. First one's 0.
And pi over 6.
Pi over 6.
Sine halves.
All right, let's do pi halves. All right. So when theta is 0, what is the valve angle measure? Pi over 4. Is it pi over 4? Negative pi over 4. If you jump down on the table there, you got a pedal angle measure of pi over 2. What's the tire valve angle measure now? Pi over 4. What's the next one? 2 pi? Just 2. All right, so somewhere around here is 2. How would you calculate, or how would you write an expression for the exact angle measure of the valve when the pedal's at 2 radians? So what would it be?
It would be theta minus, what do you want the equation?
For this one, for 2, for when theta is 2.
So it would be 2 minus pi over 4.
2 minus pi over 4 would be the valve angle measure. Agree with that? Yeah, what's the next one on the table? 4 pi over 3. It's down here. Four pi over 3. So to get the valve angle measure, if the pedal was 4 pi over 3, so you're doing the same thing for every building that table, for every entry in that table. What are you doing to the tire valve or the pedal angle measure to get the valve angle measure? All right, so the formula will be so hopefully you were thinking that, or you wrote that. It's always lagging behind pi over 4 radians. So to get its measure, you're just going to subtract pi over 4 from the pedal angle measure. It's always lagging behind pi over 4. So then the question is, are we doing sine or cosine now? Vertical height or horizontal position? Vertical height. So we know what sine looks like. Its period is 2 pi. We know that it starts at 0, right? The vertical height is 0 at the 3 o'clock position. Goes up to the highest, back to 0, down to the lowest. All right, so 2 cycles looks like this. So I'm going to repeat that over here on the right. So again, that's the same graph of sine theta. They gave that a name there. What's the name of that function? F, G, H, T of theta. Perfect. Is that right? Capital T? Okay, so on both graphs, I'm graphing T of theta. And now we want to graph, what is it called? P of, no, this would be P, right? And this would be T. P for pedal, T for tire. Okay, so if we want to track the vertical position of the tire valve above the horizontal diameter, then are we going to do sine or cosine? Sine. And what will the argument be if we're tracking the vertical position of the tire valve? What does the argument need to be? The tire valve angle, right? So whatever goes into sine, whatever angle goes into sine, that's the thing we're going to get the vertical position of. So we need that argument, or that whatever the angle is for the tire valve, to be the argument of sine. Okay, so we think about the angle. So here's where we really got to think about this. The angle starts here at 0, and the angle is increasing this way, right? So the tire valve, is it ahead or behind of the pedal? Ahead or behind? It's behind by pi over 4. That's what we said. It's behind by pi over 4. So if it's behind by pi over 4, then its cycle will start before or after the cycle of the pedal? After. Okay? So if we're looking at increasing theta along here, what does it mean for the cycle to start later? If we're looking at increasing theta this way, what does it mean for the cycle to start later? Does it start here? If thinking of increasing theta, here's where the pedal cycle starts. And the tire valve is going to start later, after. So does it start here, or does it start here A, or here B? Yeah, if it starts later, so it's going to lag behind. So its cycle is going to start like this. Do you see? So it's lagging behind. So as theta increases, the pedal angle has already started its cycle, and then later on, thinking of theta increasing left to right, later on, the tire valve. The tire valve cycle starts. So let's see that happen. So look on the right graph. Here's the pedal cycle starting, and then later on, now there's the tire valve cycle. Can you see that red graph is behind? It's lagging behind, and that's the fact that it's to the right means it comes later, it comes after. Does everybody see that? It's a really crucial thing. Why? Because we're subtracting pi over 4. So what's the natural inclination to think about that graph? That it will be which way? you'll think that it shifted left because minus is this way, right? No, but you got to think about, okay, this angle is lagging behind. So for increasing theta, its cycle is going to start later, to the right. To the right means later. It's lagging behind. So this is what happens when you subtract from your input angle to form your argument angle. And this is why it happens, okay? The graph shifts right, and then you think of, for increasing theta, its cycle is going to start that measure of the angle afterward or later. Later is to the right for increasing theta. Okay, so let's look at one more example. Okay, so here is when the pedal's in the 3 o'clock position, the valve is at pi over 3, positive pi over 3 in the first quadrant. So what can you say about the valve angle relative to the pedal angle? It's always what? He wants pi over 3 ahead. All right, so write the expression for the tire valve angle measure. Can you see that it's always pi over 3 ahead? That angle is pi over 3 ahead of our input angle theta. And so how would you write an expression for the tire valve angle measure? What would you write? He wants theta plus pi over 3. Theta plus pi over 3. Is that right? Yeah. Okay, so if we want to graph the vertical position of the tire valve as a function of the pedal angle measure, so if we want vertical position, we know that's sine. And so sine of what? Sine of the pedal angle measure or the tire valve angle measure? Tire valve, which is theta plus pi over 3. And what do we say? Is it coming ahead or behind? It's coming ahead. All right, so pedal angle measure. Here's our pedal angle measure, sine curve, right? Period is 2 pi, 2 rotations, 4 pi. So what will this graph look like? So now we want to graph the vertical position of the tire valve as a function of the pedal angle measure. How will the graph be shifted? Y to the left. It should make sense that it's to the left. Y to the left. Matt. Chad, you moved on me. That's Matt, sorry. So if it, right, he said it's ahead, so it's going to end up before. It's going to start before. So right here at angle 0, when I turn on the tire valve graph, what's going to happen? What are you going to see? It already started. See that? It's ahead, so it's already got a jump on its cycle, meaning it starts over here to the left. How far to the left is it shifted, the graph? Pi over 3. It's shifted pi over 3 to the left. So now, when I start the pedal angle measure, that tire valve is already ahead in its cycle. And so there's one full cycle of the pedal, and the tire valve has already made pi over 3 more than one cycle. So the fact that that red graph, sine of pi theta plus pi over 3, is shifted to the left, it should make perfect sense. You're adding, so that angle comes ahead of the original angle. So it's going to start earlier, which in terms of theta increasing positive, earlier is this way. Okay, anybody have a question? All right, so now we have all the pieces for being able to, given a graph, write its formula, or given a formula to sketch the graph. We've got the amplitude, we've got a vertical shift of the midline, we've got a change to the period, and then we have a horizontal shift to the argument. Okay, and we got to put all that stuff together to be able to interpret and create all these different sine and cosine curves that could model all kinds of real-world situations. So let's look at a couple examples here. So here's our general form. Here's our general form for a sine or cosine. Okay, so A sine of B times x minus c plus m. And here's a strategy for, we're going to start with problems where I'm going to give you the curve, and we're going to try to come up with that formula. Okay, so here's a strategy. Do the midline first. Okay, and then the amplitude, and then the period, and then we write it as a sine or cosine. Both are possible. And then after we get our kind of an initial sine or cosine curve, then the very last thing we'll do is we'll talk about this, is our curve ahead or behind sine or cosine. Okay? So let's just jump right into it here. No, I don't think I wanted that one. Let's see. I wanted this one. That's the one I wanted. Okay. All right, and I want those lines to be pretty faint. Okay, so the first thing we got to decide is, do the midline first. What's the midline? So the midline is halfway between the max and the min, and we know that's our vertical shift of our original sine or cosine graph. So we can write down what the max and min is first, and then from that we can get the midline. So what's the max and what's the min? So the max is 5, the min is -1, which means our midline is at halfway between those, or the average of those two. 2. So starting from a sine or cosine curve, this whole curve is shifted by how much the midline is shifted, right? So the midline is shifted up 2, +2. Okay. What's the amplitude? Remember, that's the height of the curve from our midline up to the top, or same thing as the midline down to the bottom? 3, right? So from 2 up to 5 is an amplitude of 3. And if we have circular rotation, what does that amplitude represent in circular rotation? Length of the radius, right? In whatever units you're measuring the radius in. Okay, good. All right, so for the period, so we have to decide if this period is in terms of integer values or multiples of pi, because both are possible. So right now I've got the grid at multiples of pi, or I can change the grid to make it based on integer values. So either are possible, and so you have to determine that. So is this the interval width of one cycle based on a pi scale, multiples of pi, or is it based on just whole numbers like this? So what do you look for? You look for the halfway, half a cycle, you look for a full cycle. So here's half a cycle. Is it landing on a nice integer value? No. Full cycle. No, it's like not quite halfway from 9 to 10. But if we look at the pi cycle, or the pi scale, so we can look at a full cycle. Does it land on an equal pi measurement? Yes. Same with half. It's the grid lines now are breaking this up nicely. Okay? So, what is our period in this case? Looks like 3 pi. Okay, so we'll start by writing this. What would it be easier for this one? What would be more natural, given this curve, to write it as a sine or a cosine? Why cosine? Yeah, we know our horizontal position starts at its maximum at theta equals 0. Right? So this would be more natural to write as a cosine. So we'll do that first. Okay? So we'll write it as a cosine first. So we'll call it f of theta. Amplitude? 3. We're going to write cosine of. So with cosine, is it shifted left or right? Is it lagging behind or going ahead of cosine? No, it's following exactly what our cosine pattern is, that at theta equals 0, it's at the maximum, and then heading down from there. So all we need here is we need b, theta, and what about the midline? Plus, the whole thing is shifted up 2, right? Our midline is at 2 here. So all we have left is b. Is b equal to the period? Is it equal to 3 pi? No, so we need the angle theta. So we know what the period is, and so when this angle is 3 pi, we need this whole thing to be what? So when theta equals 3 pi, we need that argument to be 2 pi, right? Because at 3 pi, we've got one full cycle, and we know that's achieved when cosine, or when the argument angle would be 2 pi. So we do b times. When we plug 3 pi into this function, we ought to get 2 pi for that argument. Because we want the period of the interval of input to give us an argument of 2 pi, so that we get one cycle. B equals 2 pi over 3 pi, or 2/3. So now we can come back up here and say 2/3. So I'll plot that again up here. So do y equals 3 cosine 2 over 3 x plus 2, and I'll do that in red, and it should land right on top of it. So if I turn it off, there's our original graph. If I turn it on, it's perfect. The red plus blue equals purple, okay? So now, what if we want to write it as a sine? Okay, what if we want to write this as a sine curve? So we got all this initial stuff is the same. The midline is still 2. The amplitude is still 3. The period was 3 pi. And that gave us a b value of, all that is the same. So now if we want to write it as a sine, we have to figure out, what we want to do first is sketch the sine curve without any shift, and then we're going to compare it to this one. So where does the sine, at theta equals 0, where does the sine start? At the minimum, at the midline, or the max? Vertical position above the horizontal diameter at 3 o'clock is midline, right? It's normally 0, but it'd be up 2 at the midline. Okay, and then it would be back to the midline at half a period here, which would be this value here. So we're going to lightly sketch what the sine would look like without any shift. That's the best sine curve I've drawn all day. Okay, and so the question is the curve that we want. The curve that we want, is it lagging behind or ahead of this one, and by how much? So is the curve, the blue curve that we're trying to write the definition for, is it ahead or behind in its cycle than this one? I'm hearing ahead. Right, because you could think about the blue one here, starting back, its cycle starts back here somewhere. So it's ahead. So here it started, and then at 0, just sine by itself started. So the one we have is ahead. How much ahead? This much. It's this far ahead, right? If you can compare the peaks there. Is that pi halves? I don't think so. It's not pi halves, right? Because this is what? This is 3 pi over 2. And this is pi halves here. We want from here to here, right? 3 pi over. Okay, so our sine curve is 3 pi over 4 ahead of just the typical sine with no shift. So now we can write this as a sine curve. Let's use g this time. So g of theta equals, amplitude is 3. We're writing it as a sine now. The value of b is the same. Plus the midline is 2. So what is our argument? Our graph is 3 pi over 4 ahead of, the angle is coming ahead of the normal sine. So plus or minus? Plus, it's ahead. Okay, make sure that you have these parentheses, right? If you're going to do it by this strategy, you need this b value times x minus. It's different if you try to do this. If you try to do bx, say, minus d as the argument, that's a different animal, and I think that's harder to track. So make sure that b is factored out of the whole x minus c. All right, so let's graph. Again, let's graph this version of it. Sine with a shift where it's coming ahead by 3 pi over 4. And it should give us the same graph. Hold on, you're going to do one, so don't pack up. So y equals 3 sine 2/3 x plus 3 pi over 4. plus 2. Lands right on top of it. Okay, so I could turn it off. There's our original blue. So the one that we just wrote, this right here, I'll plot it in red. It's correct. It lands right on top of it. Okay, I'll give you a nice easy one while I take attendance.